This is chapter number 9, ray optics and optical instruments. Okay, so before going into the depth of this chapter, let me tell you what actually the light is. I have to answer this very first question in this chapter. What actually the light is. I can give you many illustrations to explain what actually the light is. I may say one thing clearly to you people. I hope you people know the electromagnetic spectrum. The electromagnetic spectrum, that means is a collection of a huge number of wavelengths. I don't want to jump into that particular concept now. So for that reason, I just hope all you people know what actually the electromagnetic waves are. Among those electromagnetic waves, there is a particular region in the middle portion. Okay, so in the middle portion we are having a particular region of wavelength. There is a range of wavelength. Let me write those wavelength range. So the wavelength range is from approximately 400 nanometer to approximately 700 nanometer. So the wavelengths of the electromagnetic waves, the middle portion of the electromagnetic spectrum, that is roughly 400 nanometer to 700 nanometer. Okay, so this portion of the electromagnetic spectrum is called now visible light. Visible light. And actually, now in this particular chapter, we deal only with this range. Obviously, in that electromagnetic spectrum, the wavelengths or the electromagnetic waves before 400 nanometer, we call them ultraviolet, and beyond this 700 nanometer, they are infrared and some others. It extends on both sides. But I am much interested only about this range of wavelength. So 400 to 700 nanometer, so which is visible to human eye. So human eye can get those wavelengths and collect informations from our surroundings. So we can watch what is happening around us. So this particular range of electromagnetic waves will produce sensation in our eyes. And finally, we will get the image of our surroundings that is, computerized in recalculated in our brain, and a clear-cut image is generated. And finally, we will observe the surroundings. No doubt. So this 400 nanometer is for violet color, and this 700 is for red color. So violet is 400 and 700 is for red color, and in between, of course, you know this one, Weber-Gaillard. So violet, indigo, blue, green, yellow, orange, and finally red. So Weber-Gaillard. So as the wavelength increase 400 to 700, the color of appearance changes from violet to red. So this portion of electromagnetic spectrum is now most needed for this particular chapter. I use many times two terms: ray of light and beam of light. We will get definitions for these terms in our NCERT, no doubt. But I am going to explain you what actually these things are. Most of the time, we people use such terms: ray of light and beam of light. And in market we are, we can purchase some laser torches. A very sharp beam of laser torch that we can get. So such kind of laser pointer, so it will produce, if I call this a pointer laser, so it will send a particular pointed light. So that path, the path I can call a light ray. So briefly, nothing but the path of light. Okay, so path of light is usually said light rays. A singular light ray and multiple light rays. Now beam. Now I have to talk about beam. If you are using a big torch, it's a torch. So it may produce, a parallel light beams, light rays like this, parallel light rays. The collection of those parallel light rays together you can call beam of light. So this is a brief explanation about ray of light and beam of light. Two more terms we usually use in this chapter. So now denser medium and rarer medium. So two terms, denser medium and rarer medium. Usually the term denser medium means a kind of medium in which light passes slowly. It should move slow in that medium. So that particular medium we technically say denser medium. I may give you several examples. For example, in comparison with air, glass is a denser medium, water denser medium. So look here, a big clue I could give you. So between glass and water, glass is denser than water. If you talk about water and air, so water becomes the denser and air becomes the rarer. This is how we have to guess, we have to understand. So then it is a rarer medium. So it is a contradictory definition of this. So it is a light ray, light passes faster. That medium, the rarer medium, light should move, light should pass much faster. Such kind of mediums are usually we call rarer medium. So I already said, usually I may say air is rarer in comparison of other mediums like water. When you compare water with glass, so water is a rarer medium and glass becomes denser medium. So this is how we have to guess about these things. Now I am talking about speed of light. It's amazing speed. A light ray can pass in vacuum with the greatest speed ever known. And that speed is roughly 3 into 10 power 8 meter per second. In your syllabus, of course, the standard value of the speed of light in vacuum takes many decimal places. I'll refer this number. It is 2.99792.458 into 10 power 8 meter per second. So we cannot recall this huge number. So no doubt here is the decimal point and many decimal places. I feel it is very difficult to recall this number all the time. So probably this could be the reason. So we just take this number approximately 3 into 10 power 8 meter per second. This is the speed of light in vacuum. This is the speed of light in vacuum, greatest speed that we ever know. And this particular number, 3 into 10 power 8 meter per second, we usually represent it by the small letter c. So c stands for speed of light in vacuum, it is 3 into 10 power 8 meter per second, greatest speed. In other mediums, in other optical medium like glass, water, and some quartz. So in all these media, the speed of light is usually we write v, and this is less than c. That means in glass, water, quartz, and any other optical medium other than vacuum, so can we call vacuum as a medium? That you have to think further. Well, so glass, water, quartz, and some other optical medium like oil, something, whatever it is. So in those media, the speed of light is less than 3 into 10 power 8 meter per second. So V is less than 3 into 10 power 8 meter per second. I am having two more definitions for you. Absolute refractive index and relative refractive index. What actually the definition of absolute refractive index? Say I am having some medium. For example, here is some medium. Whatever it is, it may be a glass or something else. So the light moves here in this medium with a speed v. Definitely this v is less than c. V is less than c. So this is the speed of light inside that medium. So now we define absolute refractive index of this medium. So absolute refractive index of this medium. Usually we denote it by the letter n, or somebody may write the term mu, the symbol mu. So n, absolute refractive index of this medium. Whether it is, if it is glass, I have to say absolute refractive index of glass. If I am having water, so absolute refractive index of water. This is how I have to read this notation. Absolute refractive index of this medium n is equals, it is the ratio of, see, it is the ratio of speed of light in vacuum, which is c, 3 into 10 power 8 meter per second, that is c, divided by speed of the light in this medium. So that ratio I have to call absolute refractive index. So this is how I have to read that n. Now look about one factor. This c or this v are speeds, means they are same quantity. They are same quantities. For that reason, the dimensions in numerator and denominator get cancelled, and this n has no dimension, no dimensions, otherwise no unit. So this n is having no unit. N is having no unit. Well, so that's all about absolute refractive index. Let me take one more definition. It is a relative refractive index. So for that, I have to think about a border. So on this side, here is medium 1. On this side, here is medium 2. If I say the speed of light in first medium is v1 and speed of light in the second medium is v2. Now I can define two terms n1 and n2, and these two terms are absolute refractive indices, index singular, indices plural, right? So n1 and n2 absolute refractive indices of medium 1 and medium 2. So now, since the light ray is moving from, if I am guessing, so light is moving from medium 1 to medium 2. This is how light is moving. So light is moving. Let me take it from medium 1 to medium 2. Then I can write n one, 2. That means light is moving from medium 1 to medium 2. This is how I have to write. So this is equal to n2 by n1. So be careful about the notation. n1, 2. So the first subscript means where the light was. Second subscript means where the light is entering. So n1, 2. That is equals n2 by n1. It is not n1 by n2. If you write n1 by n2, that will be different. Okay, let me talk about that later. So now I am getting n2 by n1. How you have to read it? So this is nothing but refractive index of medium 2 with respect to medium 1. So refractive index of medium 2 with respect to medium 1. This is how you have to read this notation. If you write it reverse, n1 by n2, that will be different meaning. So refractive index of medium 2 with respect to medium 1 should be written like this only. So be careful. And one more time you can see, so already n2, that means absolute refractive index of medium 2, n1 absolute refractive index of medium 1, they have no individual units. For that reason, one more time, this ratio has no unit or no dimension or no dimensions. So be careful. So this ratio is one more time having no unit, no dimension. Okay. So if you write n 2, 1, what is the meaning? The meaning is light is now moving from medium 2 to medium 1. It is not from medium 1 to medium 2. So be careful. So you have to take care each time when you write this. When light moves from medium 2 to medium 1, light is now moving from medium 2 to medium 1, then you can write n2, that is n1 by n2. This is how you have to write. And one thing I will make you clear, the value of absolute refractive index for vacuum is 1. So absolute refractive index of vacuum is 1. So n is equal to 1 for vacuum. And what about air? So I will make you clear. In air, what happens in air? There is a slight decrease in the speed of light. That means in vacuum, so the speed is 3 into 10 power 8 meter per second. So this is in vacuum. But in air, the speed is just less than this. It's not 3 into 10 power 8 in air. So that means for air, n is equals to C divided by V, and V is less than C. For this, I should take care. So n is just over 1. But for most of the cases, we take n is approximately 1 for air. We take n is approximately equal to 1 in most of the situations, because The speed of light in vacuum is 3 into 10 power 8 and in air it is just less than 3 into 10 power 8. The ratio will be very close to 1. For that reason, it is almost 1. So here is what you call sign convention. Let us learn what about the sign convention your syllabus tells. So sign conventions, there are 3 sign conventions we use in measure. So first point is all distances are measured from pole and along principal axis. Distance in the direction of light positive and in opposite it is negative. Heights above principal axis is positive and below it is negative. Let me explain it. For that, I am having 2 drawings for you. One is here and one is here. And this kind of one mirror we call concave mirror and this kind of one mirror we call convex mirror. I may need both these kinds of mirrors to learn about these sign conventions. First of all, here is what I call a ray of light. So, which is coming. So, always you have to represent a line saying a ray of light with an arrow. Otherwise, it never be called a light ray. So, be careful about this point. In all your tests and examinations, whenever you draw light drawing, ray drawing, so you must show arrow mark in your picture. Otherwise, definitely there is a chance of losing marks. So, a light ray is coming and it's hitting this mirror and something happens afterwards. Let you learn it later. So, what actually the thing is saying? Now, in both of the mirrors, concave or convex, we take this line as the principal axis. What actually the principal axis is? This is nothing but, this is nothing but a line which is normal to the surface. To the surface. For this surface at this point, okay, so if I draw a tangent, for this tangent, here is the tangent, right? Okay, here is the tangent. For that tangent, this line is perpendicular. What happens then? If a light ray comes along this line, and makes an incidence, that means hitting the mirror at this point, it will go back. It will go back along the same line. Okay, so have you learned what happened? So light ray comes along this line and hits the mirror and goes back along the same direction. Such kind of a line we usually call principal axis, and this axis exists both in concave as well as convex mirrors. Well, so what actually the point 1 says? We measure all distances, whether it is left to the mirror or right to the mirror, in either of the cases. We take this point as P. P stands for pole, which is existing here. P. The letter P is pole. This is the reference point for all my measurements about distances. So this is what you are seeing here in the first point. All distances are measured from pole and along principal axis. All distances always measured along principal axis, whether it is on left side or right side. So let me tell about the second point. Be careful here. Distance in the direction of light is positive. So if I measure distance in the direction of light, should be very careful. We are measuring all distances from the pole. I hope nothing could be explained here. See here, if this is the pole, here is something. Say it's an image of the object. If you want to measure the distance of this image from the mirror, I have to measure this distance. this distance. This is called image distance. Image distance. So this image distance is measured in this direction, means from pole to my right. So this distance is taken positive because light is also moving in the same direction. This is the incident light. So incident light is moving in the same direction. So light is moving in the same direction as my measurement. So that means this distance is taken positive. Well, so otherwise it is in opposite direction, it is negative. So opposite direction it is negative. See, in this situation of the mirror, let me say this is the image. So image is here. So for this, so this distance becomes image distance. This is image distance. So this image distance is measured. This image distance is from pole. So that means from pole, the distance of the image is this, and this image distance is negative because light is moving in this direction and my measurement from the pole is to my left. It should be taken negative. So this is all about the point number 2. So let me take the third point. Heights above principal axis positive. See either of these pictures. So here the height, say this one, this height is taken positive height. Well, this is what they are saying. Heights above principal axis. This height is also positive because if we measure the height from the principal axis, this should be taken positive in accordance with the convention. And what about the height below? The height below the principal axis is negative. It is minus h. This is minus h. And this is positive. So this is plus h. So for object, we take HO. For image, we take HI. So this is object. If I say this is the object, this is HO. If I say this is the image, this is HI. HO is positive. HI is negative. Here HO is positive. HI is also positive. This is how you have to learn about all sign conventions. Here are some definitions for you. Center of curvature C, radius of curvature R, principal focus F, focal length F. For that, I am having a kind of mirror, a curved mirror. If I extend this portion to complete a big circle like this, so here becomes a big circle. Here is a big circle. If you know where actually the center of this circle is, and this is what we know as center of curvature. So this is how you have to guess the center of curvature. And the distance between the center of curvature and the pole lies here. The distance between center of curvature and the pole. And this distance we call the radius of curvature R. So radius of curvature is R. And next is principal focus. Now what actually happens? To understand the principal focus, I have to adjust something in the picture. Say this is the principal axis. Here is no importance of the line beyond this mirror. So let me use it only to say it is principal axis. This line stands for a principal axis. So now, if I say the light is moving, it is incidenting from a long distance on the mirror. So light is coming from a distant source. So light is from, infinite source at infinite distance. Source at infinite distance. Infinite distance. When the light source is at infinite distance, the beams of otherwise the rays of light are exist in parallel. So these lines are in parallel with the principal axis. So such light rays when hit the mirror, when they hit the mirror, they focus at some point. That means they reflect to one common point, one common point. So if you want more light rays, you can draw. So all light rays should pass through such a kind of one common point. Here is the common point. Look here, this common point of meeting, so that is existing on the principal axis itself and within C and P somewhere here. So this point I should call principal focus. Principal focus, letter F. So this is principal focus. And the distance between the center of curvature means this one and the pole this one, this distance is called focal length of the mirror. Is called the focal length of the mirror. So you must remember these very important definitions and meanings for the future classes. Having this picture on the board, you are seeing a kind of curved mirror here. We call it concave mirror. Concave mirror. And we already know this line. This is the principal axis. Principal axis. And here is the object. So object is here. Object is above the principal axis. And to know where actually the final image is going to appear, I need at least 2 light rays. At least 2 light rays. The first light ray is moving from this peak of the object to the mirror in parallel with the principal axis. And it goes and makes a reflection, and that light ray, the reflected light ray from the mirror, should pass through the principal focus of the mirror and it is moving further. We are not bothering what is happening next. And the second light ray should move from the same peak of the object through the center of curvature of the mirror. The point of center of curvature of the mirror, look here, C. So that light ray, that will meet this first light ray, the reflected first light ray here. Where actually they meet, you may guess the final image will be there. So this is the position of the final image, and when you draw such a kind of one arrow mark like this one, that indicates the image. Okay, so from principal axis to the point of intersection, so that is the position of the image, and you can see in this notation of the picture, the image is inverted. It is below the principal axis. So you are seeing the image inverted. The object is erect, but the image is inverted. You are seeing it in the inverted form. Okay, so upside down. Well, so now I have to form you the mirror equation. So learn just this equation for the examination purpose. See, for that I have to explain you something more, that is P to F. The distance P to F. This is focal length. Focal length of the mirror F, and from P to C, so from P to C, it is the radius of curvature. It is the radius of curvature R. And one more thing you must know, that is the distances like object distance and image distance. I call this as something like O and this I. Okay, so PO is the length or distance called object distance, distance of the object distance. Symbolically, most of the time we use the symbol U. And PI is this one, P to I distance. Be careful, we always measure the distance from pole. So PI, that is image distance. Image distance. And that image distance is V. That image distance is V, let it be. One thing you have to know here, you have to note. In such a curved mirrors, always, F is equals R divided by 2. So F is equals R divided by 2. You must remember this equation. So there is no need of proving this one, but you must remember F is equals R by 2 always for spherical mirrors or curved mirrors. Well, so having said this, let me move directly into the mirror equation, and the mirror equation is, so definitely 1 by F is equals 1 by U plus 1 divided by V. So this particular relation we call the mirror equation. The mirror equation, we call it mirror equation, and the mirror equation is very important for the purpose of learning as well as examination. F, the meaning of F is here, U is here, and V is here. So all terms are noun. So once you know any two parameters, you can find the third one. This is how you have to make use of this equation. So this is called mirror equation. Finally, I have to take you to the term linear magnification. You know what actually happens when we use such kind of curved mirrors? The size of the image may not be exactly equal to the size of the object. The size of the image may be smaller than the object, equal to the size of the object. Otherwise, it may be greater than the size of the object. So any of this. So for that purpose, what I have to right now is, linear magnification. Linear magnification. M is equals, we write it, M is equals, say some H dash divided by H, which is equals minus V divided by U. So you have to know this one, M is equals, M stands for linear magnification of this mirror now. So linear magnification M is equals H dash divided by H, and that is equals minus V divided by U. So minus V divided by, here is the negative sign, minus V divided by U. Be careful, here there is no negative sign. So M is simply equals H dash divided by H, that is further equal to minus V divided by H. V is this one, which is image distance, U is object distance, H dash and H. Here in standard we take H as the height of the object and H dash as the height of the image. So I should write it here. So H dash, height of the image or size, whatever the term I use, height of the image, and H is height of the object. So if you know these terms, definitely you can do answer for many of the questions in the examination, as well as it helps you to do numerical problems and to answer many multiple choice questions.